Our last speaker of the day is Kaveh Mousavand. He's going to talk about brick-direct algebras and their applications.
I wish to start by thanking the organizers for giving me the opportunity to speak here, and also the ICTS administration and team for their hospitality. This is my second visit after 7 years to ICTS, and from both occasions I've been having a good time. I've been benefiting a lot. So today's talk, I come from representation theory of associative algebras, finite dimensional algebras. And what I'm going to share with you is based upon a joint work, a recent joint work with Sota Asai, Osamu Iyama, and Charles Paquette, and objectives were. And then what we did, probably most of the first few lines will not fall in the scope of your interest if you're not coming from representation theory of associative algebras. So please do not feel discouraged immediately if terms are not familiar, because I'm going to select one part which is a lot more tractable, falls into the common knowledge of algebra. And I believe it's a novel thing that it may be worth considering. So what was the project about? The project was originally the study of lattice of torsion classes over finite dimensional algebras. If you're a combinatorialist, you're kind of inclined to think about lattice theory or torsion classes if you're working in homological algebra or representation theory of associative algebras. This can be an interesting goal, and otherwise, I assume it may not necessarily appeal to you right away. So what did we want to do more specifically? We wanted to give a representation theoretical / homological / categorical interpretation of a phenomenon in lattice theory, which is called left modular elements. What are they? Why are they important? I'm not going to talk about them today, but I'm putting them on the screen. So if anything intersects your interest and you want to talk to me during my stay, during your stay, I'll be delighted to do so. We wanted to describe left modular elements in terms of certain categorical phenomena. And we wanted to further classify what lattice of torsion classes are left modular extremal or trine. Again, may not be necessarily the most familiar terms to you. What was the methodology? Well, we generalized two phenomena, classical in representation theory from 60s, 70s, 80s. One of them was we introduced the notion of brick splitting torsion pairs, which is a generalization of classical splitting torsion pairs. And we also generalized the notion of representation-directed algebras to what we introduced as brick-directed algebras. And what I'm going to do today is actually to focus on this thing, brick-directed algebra, a tool that actually proved to be important enough to somehow consider it a little bit more carefully. So setting and notation and convention will be as following. K, for the sake of tractability, you can drop the assumption that K is algebraically closed, but for the sake of tractability in this talk, let's assume K is an algebraically closed field. Let's assume A is an associative basic connected finite dimensional algebra. You can, again, drop the assumption that A is basic and connected. You can turn your problem into this setting, but what you need to assume is you're working with a finite dimensional associative algebra over an algebraically closed field. By mod of A, I denote the category of finitely generated left A modules, and by ind of A, I denote the set of all isoclasses of indecomposables. Classically, an algebra is called representation finite if it admits only finitely many isoclasses of indecomposables. Let me establish a language from pure algebraic setting to the more combinatorial framework, which may actually overlap your interests. Moving to the realm of quivers and their representations, for which I just recall this fundamental theorem of Gabriel, which says, if you're working with a finite quiver, quiver is nothing but a directed graph, as we know. If you're working with a finite quiver and you look at the corresponding path algebra, then that corresponding path algebra has only finitely many indecomposables, up to isoclass, if and only if the quiver is ADE, Incan. So, well, something that we all care about. And the second part is even more fundamental, because it says if you start from any algebra in that generality that I talked about above, you can find a unique quiver, you can find an ideal in the corresponding path algebra, such that the algebra that you started from can be realized as a quotient of the path algebra that you construct via that unique quiver. So this is good because, well, additionally, you get an equivalence of a billion categories. Module category that I care about and representations of this bound quiver subject to the relations. Henceforth, therefore, we can assume that every algebra is given as a quotient of a path algebra, and every module that I care about, you may care about, is nothing but a bunch of vector spaces at certain vertices and linear maps between them. Representation theory of quivers, okay? That was just like the dictionary that I use freely because I want to present concrete examples, and my concrete examples are over quivers if you want to actually compute something, as you already see something I've drawn on the board. So background materials about the topic of today. A definition is very simple that I begin with. In your module category, by the way, if I'm too loud, kindly let me know. I can adjust my mic. I don't want to scream and like make you suffer for 20 minutes. So a path in the module category is nothing but a sequence of non-zero, non-invertible morphisms between indecomposables. You have a sequence x0, x1, x2, all of which are indecomposables, and you have a bunch of morphisms between them if i's are non-zero and non-isomorphic. And then you call a path naturally a cycle if it begins at and ends at the same iso class of indecomposables, meaning that x0 and xm are isomorphic. This is called the cycle. An indecomposable module is called a directing module if it doesn't lie on any cycle in your module category. And if every indecomposable of your algebra satisfies this outstanding property, then you call that algebra representation directed, meaning that no indecomposable falls on a cycle. Equivalently, an algebra is representation directed if there is no cycle whatsoever at all inside your module category. If any part of this definition is subtle or unclear, kindly let me know, because this is what we want to build upon. As you see, nothing is very technical, just general module theory so far. Example and non-examples. So I begin with a useful example, which is minimally designed to work during this talk. I said I start from a quiver. I construct a path algebra. For those more confident with the path algebra and the representation theory, you can immediately see that the path algebra that I construct over this quiver is infinite dimensional, because I have this loop, and then hence I have larger and larger and larger circuits, okay? So if I'm considering the path algebra AQ, I'm in the realm of infinite dimensional algebras. I said I want to take a quotient of that, and my ideal here is generated. I write compositions as following. Alpha composed with beta, I write it as alpha beta, and beta beta, which is beta squared. So now I am down to only literally two non-lazy paths. I have lazy path 1, which is just hopping at 1, lazy path 2, hopping at 2, one path alpha. It would compose with beta if I hadn't introduced this relation, but now it cannot. And beta cannot compose with itself for a second time. Hence, I'm down to alpha, beta, E1, E2 as the only basis elements. So a basis for A here is E1, lazy path at 1, E2, alpha and beta. And this allows you to immediately conclude that the dimension of A as a vector space is 4. Okay. Now I want to look at the representations of this algebra. I have computed that. In various ways you can do so. You can list all the indecomposables. You have 5 of them. If you're comfortable with this notation, I mean simple at 1, simple at 2, projective at 1, projective at 2, and injective at 2. You may wonder, what about injective at 1? It's actually S1. Okay, so, and then this is the radical filtration of these modules. If you're, again, familiar with the radical filtration. I've written it in different formats, so whichever better appeals to you, you can work with them. Now, let me write them explicitly. This is S1, which means K0, and the map between as non-zero and as 0 is evidently 0. So I may stop writing 0 maps. And then I had P1, yes, which is K1, and this is 0. And I have P2, which is here K squared, 0. So this map is evidently 0. And this one is, and I have I1, excuse me, I2. So this is P2, and I have I2, which is K squared here, K here. And this one I have chosen this pair of matrices. So if you want to, which one? P. Oh, thank you. Of course. Good catch. Excellent. If there's any other typo or error in my writing example here, kindly let me know. So now we have an explicit computation of whatever I need to play with for the next few minutes. And let's look at a path. And I'm intentionally creating a long path because I want to point out something to you. So be patient with me for a few seconds. So as you see, this is P1, this is I1, excuse me, I2, this is S2, this is P1, this is I2, this is S2. That is my reminder that I should go faster. This is S2, this is P2. Okay. Okay, so now, as you see, the morphisms, these are the same in the composables that I'm playing with. The morphisms, none of them is 0, none of them is isomorphism. The easy way to check is like they are of different dimensions as you go up, so they cannot be isomorphisms. And this is a path. And you see that, in fact, in this path, you can identify various cycles of interest. For example, you can have a cycle P1 to P1, I2 to I2, S2 to S2. You have, again, P2 to P2. So it seems that pretty much everything lies on the cycle, right? So this easy computation shows that S2, P1, I2, P2 are not directing modules. And if you do a little bit of computation, you realize that the only directing module in this example, only directing, is S1, which you cannot actually put on a cycle. And then there's another example. If you like, you can compute this for yourself, where I is alpha, beta, and beta, alpha. And you have 4 indecomposables, and you can check which one lie on a cycle and which one does not. Actually, that's a very useful example. So let me proceed. I already forgot my here. So, what is good about representation directed or directing modules? Yeah. Good catch. Yes. For an algebra, each directing module is uniquely determined by its dimension vector. Meaning that if you know the information at every vertex, how many copies of K you have at a vertex, you can uniquely determine that module. This is a very rare property. Okay? A path algebra, KQ, is representation directed if and only if it's a Dinkin-Quiver. So if you don't have any relation, Dinkin-Quivers are the only ones for which you have every indecomposable directing. Every representation-directed algebra is representation finite. You can prove it in various ways. Either you use a very heavy theorem such as Brouwer-Thrall theorem 2, or more elementary methods that are available in the literature. Okay. So the fourth one is, if your algebra is representation directed, then your quiver is triangular, cannot have any cycle. You cannot have a cyclic walk through the arrows whatsoever. So you see that it's a pretty restrictive condition. Some remarks, converse of one is not true in general. If you can uniquely determine your indecomposable by the dimension vector, it doesn't mean that it's directing. I don't have enough time to present concrete examples, but I have concrete examples in my notes if you're interested. Remark 2 is representation-directed algebras can be seen as a generalization of Dinkin type, because every Dinkin-Quiver is representation-directed, but there are representation-directed algebras which are not Dinkin. An easy example that you can convince yourself, oh, let me write it. I'm so used to notations. So consider AQ over relation alpha beta. This is your Q. This is representation directed, but evidently not Dinkin because it has not hereditary. The converse of 3 is not true in general. Also, converse of 4 is also not true in general. So there are facts. But what is conceptually interesting about directing modules and representation-directed algebras, they're very, very decisive in the study of tilted algebras, which we are not going to delve into in this talk. But that is some connection that others may care about. So a modern analog of representation-directed algebras, I'm going to go a little bit faster because now we have the tools and techniques. So I just recall that a module is called classically or traditionally a brick, or sometimes a Shor representation, if the endomorphism algebra is trivial, meaning that every non-zero morphism from that module to itself is invertible, is isomorphic. It's called a brick or Shor representations. These are very important modules for various reasons. But to fix the notation, by brick of A, I denote the set of all isoclasses of bricks of the category that I care about. And the algebra is called brick finite if you only have finitely many isoclasses of bricks. Bricks are very important. Every brick is evidently indecomposable. Hence, every representation finite algebra is brick finite, but the converse is very far from true. And they have, there are many open conjectures about the behavior of bricks on these topics. If you want to know more, just you can look at one of my recent work or the survey that we recently wrote on bricks. Now I'm going to introduce brick-directed algebras. What was the path? We just looked at it. Look at the brick path. Just a sequence of maps, non-zero, non-invertible, between bricks. And a brick cycle when the brick path closes. And the algebra is called brick-directed if every brick, but if no brick lies on a brick cycle. Does the terminology and definition make sense? Because if it's unclear, again, I can elaborate. But it's just a brick analog of what we just discussed. Now, I had a bunch of remarks, but I want to visualize the remarks instead of running through them. what we did is we started from an algebra. We have the set of all indecomposables. We have n many simples if our algebra is of rank n. And then we have directing modules, a bunch of indecomposables, some of which are simple, some of which may not be simple, as we saw over there. There are simple modules which are not directing in particular. And then bricks contain simultaneously all the simples and all the directing modules and a lot of more indecomposables, but it's a subset of indecomposables. And now let's look at the first result. Earlier we saw, I recall what we saw earlier. A path algebra was representation directed if and only if the quiver was Dinkin-quiver. By just changing your perspective and focusing on all indecomposables and caring about whether or not they fall on a cycle or something, we looked at bricks and looked at whether or not they fall on a cycle of bricks. Then you have this proposition which says a path algebra is brick directed if and only if your quiver is either Dinkin or the Kronecker quiver. If you don't recognize the term Kronecker, it's nothing but this quiver. 2 vertices and 2 arrows. This is called Kronecker quiver. So you already get something new. And remember, this one has infinitely many indecomposables and infinitely many bricks. So if you just think about it for a second, I just gave you a definition which required to check every brick, whether or not it falls on a cycle, and I have infinitely many bricks. So there must be a systematic way to decide whether or not an algebra is brick directed. Okay, so this is one gain that you have immediately. And this particularly implies that brick-directed algebras generalize representation-directed algebras. Because remember, representation-directed algebras were representation finite, but this example is even brick infinite, not only representation infinite, but brick infinite. To continue with a little bit of more result, remember that a quiver was called triangular if it had no cycle. And we call it weakly triangular if it has no cycle other than possibly loops. Okay, loops, arrows that start and end at the same vertex. We call such quivers as weakly triangular. And now here is the second result, that an algebra A, if it's brick directed, and I recall the motivation. The algebra which was representation directed, a loop or many loops, but no longer cycle. So the quiver is a little bit more flexible than what it was. Finally, let me know how much time I have, so I plan the rest of it accordingly. Would you let me? Is that exactly the time indicated on? Okay. So, of course, how many loops would you like? Oh, that one. That one is it's not representation directed, but it's a brick directed. One loop, it works. Actually, this is, yeah. Put as many as you like, alpha 1 to alpha m for any m, but quotient out by I alpha j's. Okay? This has only one brick, and it's brick directed. So you see, it goes wild even as an algebra. So this is the second result. And the third result, I must rush a little bit. The third result, I try to motivate it again by recalling some facts that we had seen, that for rep-directed algebra, every indecomposable was uniquely determined by the dimension vector. For every brick finite brick-directed algebra, the very same fact holds. And it's a very rare condition. If you want to know what it geometrically means at the level of representation variety of algebras, I can reword it in that term. May I take 30 seconds to finish? Thank you. I can reword this result in terms of representation variety of algebras and the orbits of bricks and such, but I postpone it until follow-up discussion. It's a very non-trivial fact, actually. Maybe this is the best thing that I wanted to share with you, admittedly, today. And then to finish, I have examples. I finish with this kind of big theorem. It says, if you take any positive integer n, you can construct explicitly via construction that we have given in the paper, an algebra which is brick-directed of rank n of any of these types. Representation finite algebra brick-directed of rank n. Brick finite tame algebra of rank n. Brick infinite tame algebra of rank n. Brick finite wild algebra. So we can construct any sort of algebra of rank n which is brick-directed, as soon as we fix. So they are everywhere. Brick-directed algebras are everywhere, in every rank and of any type that you like. And that's why I'm convinced that actually they are worth studying beyond the capacity that we exploited them in this project. So I finish with this schematic presentation of what we looked at. So you just scan it. Even if there were parts that I didn't elaborate on sufficiently well, I apologize for that, and I thank you for your attention.
Are there any comments or questions?
You can construct brick-directed algebra of your arbitrary global dimension. Hereditary, global dimension 1, 2, 3, M infinite. You can construct it explicitly. So that's another freedom that comes with. Of course, thank you for asking that. So for every fixed dimension, you can look at all modules of that dimension over your algebra. It refines into finitely many components connected, because that forms a big affine array. It refines into finitely many connected components, each of which is determined by the dimension vector. And inside each dimension vector, you have orbits of modules, right? This theorem, it says, when you pick up your arbitrary dimension vector over a finite brick-directed algebra, inside that variety, there can be at most one brick. We know that in every irreducible component, you can have 0 brick, 1 brick, or infinitely many bricks. If you're brick finite, inside each irreducible component, you certainly have at most 1 brick. But this one says you have inside your dimension vector, which itself contains different number of irreducible components, overall, you have at most 1 brick. And this perspective is something that we hope to generalize when we look at brick-infinite brick-directed algebra. That, in fact, for each dimension vector, even if you have infinitely many bricks, they fall into one irreducible component. I can elaborate on this very last statement, which was quite subtle, in more details if you're interested.
If there's no more question, let's take the speaker again.